Is this thing on? Yes, it is. So hello, everyone. Good morning. I also find it quite funny that I was the last one to join this crew, and I'm almost the first one to speak at it. So, and that whole talk will be a little bit like that as well. So don't expect necessarily a linear narrative for the next 40 minutes or so. So, and also welcome to Religious Studies 101. It's actually, everyone I think knows about the Tower of Babel, also auch called der Turm von Babel in Deutsch. Yeah. So this is a famous quote from the Bible, and it's often used about to kind of describe the punishment of humanity for trying to be too audacious and trying to kind of mimic God's work, and therefore needs to be put down. So, but I'm here not obviously talking about religion, but another interpretation of the Tower of Babel is the fragmentation of languages, which was actually the kind of implementation of that punishment in the Bible. And if you take a more evolutionary point of view, you could actually say this was one of the best things which happened to our species, because it created those different mindsets and philosophies and different cultures and different ways of thinking about the world, which also helped us indirectly to succeed as a species, and at least some of us overcome some problems which other cultures maybe haven't reached yet, or basically balances all each other out. By having different approaches rather than just one approach, we as a species together became far more stable. So it's really mainly about languages of all sorts, programming languages, natural languages, design languages, and all baggage related to it. So one of my famous, or not famous, one of my most popular mantras in my own life is this Wittgenstein quote, which I think is so true. No matter what you do, if you can't express a thought, and we need language to express thoughts, we will have reached the horizons of our understanding. And the only way to overcome that horizon is to learn new languages or improve our mastering of a language we've been given already. So, and then you can also analyze language from a more linguistic point of view, and I'm not a linguist by any means at all. I only have a hobby interest, really, so probably experts will put me down if I try to explain this in more detail. But what I like about it, that there is this fundamental atomic part of language, which are our syllables, which create sound. And a lot of religious cultures basically have those processes where they gather as group and they have those long strings of syllables where they kind of chant for hours and hours. And where lots of studies have been done where it has been figured out that no matter what people's backgrounds are, we kind of converge towards the same sounds made on that fundamental level, which is almost on an unconscious level in a trance state. And that kind of inspired me to also think about how that applies to programming, because that's what I do most of the time. And that's maybe a little bit of a stretch, but I think there's something similar in programming, and maybe some people remember that. These are really the digital syllables, zeros and ones, represented as two different frequencies, but played so loud and so fast that they form those kind of pattern noises. So from just zeros and ones, obviously, it's a very painful way of communicating. So in order for us humans to start talking to machines, we needed to invent an alphabet. We needed to invent an alphabet to speak to other people back in the distant past. So in computing, the first thing we did was to take those zeros and ones and group them into groups of 4, which gives us then an alphabet of 16 symbols, which is also called the hexadecimal number system. And with that, you can actually already write a form of text. And you can do that on paper. And I've done that. This is how I started programming when I was 13. So we had 1 hour computer time a week, and all programming basically happened with pen and paper for the rest of the time. So these are some scans. That's the instruction table of the 6502 processor, which was in the Atari 800. And that was my manual to the hardware. And having no previous experience of programming, we basically spent our first few years like that. And as you can tell, that is a mixture of programming. Here I started in doing my own version of Photoshop, 5 years before Photoshop came out. And these were the tool icons for the different things you could do with that program. Some level maps for games I wanted to do, never finished. But it really boils down to this, in my opinion. And even with that super limited set of tools available, and also a machine which is about 1,000 or 2,000 times slower than what we have available these days, we ended up being able to do things like that. So this is running on an Atari emulator on my Mac now. But that's something I did when I was 18. And it's amazing, huh? Scrolling text. So that was my first 3D graphics. The background image has been placed or created pixel by pixel with a joystick. It took about 2 weeks to create. You can see there are only 4 colors for every pixel line. So you had to really exploit hardware. You had to become a kind of hacker to create, for instance, those raster bars in the bottom. And that quickly became a skill which everyone knew how to do that. So that kind of propagated then the whole demo scene forward, which still exists and which will come back later. When I did my A-levels, I've been commissioned, or during I did my A-levels, being commissioned by a game company in Frankfurt to create a clone of Lemmings, commercial clone, and I almost failed because of that. Had to redo my maths test. So all those things were done on machines which were super limited. And I really just want to give this as a frame of reference, because these days we so often moan how hard it is to learn programming, and we actually are using languages which are 100 times more human adjusted already. And it's all a little bit relative. And I'm not saying that this is the right way, but when I went to college, our professor, he started talking about Alan Perlis quite often, and I only got back to him recently again, earlier, like a few years ago, reading some of his quotes, and he comes up with amazing things like that, which I fully share that view. I better don't read that out with my German accent. But you get the idea. And what that all boils down to is really this. And I think this is one of the hardest lessons to learn and also to accept, that when we work with computers, or if we try to have computers do what we have in our heads, it's never the machine's fault. It is always human fault. And this is a bitter pill to swallow. He also said this: a language which doesn't affect the way you think about programming is not worth knowing. But I think you can actually leave out the word programming here, because a language which doesn't affect the way you think in general is not worth knowing. So most of us don't speak too many languages in terms of natural languages. But if you talk about programming languages, you can really see that every single language contributes a quite unique idea of the world. So it's about worldviews. So the Western philosophy can be a little bit summarized like this. We look at the world, we try to decompose it into tiny, tiny parts, and then we spread them all out and look at them, and we think we understand what's going on. And that's really only, in my opinion, half the story. And it really misses that opportunity of actually thinking about all the processes which initially related and came together to form objects. So there's here, you can do this on the nano level as well, where we start doing now really manipulating molecular structures to build a new world, a synthetic world, from scratch, from the tiniest elements we actually can access at the moment. So, and it's really about this world building also. If you think about what you do in the computer, we start basically with nothing, an empty memory, an empty slate. And by thinking about what the different processes are, we can build up those higher dimensional spaces. And often that also means that for every of those transformation steps, there's either some form of data being consumed or emitted, and that data can be reused for all sorts of other things. And when people talk about big data, this is partly what they are talking about, to harness all those kind of invisible data emissions, which we right now haven't had the capacity to actually process yet. So, and a lot of people, when we talk about programming, it's not necessarily just machines, it's also, for instance, what Skylar Tippett does at the MIT Self-Assembly Lab, where they talk about recreating new molecular items, or not really molecular, molecules or forms of a kind, but to think about how you can use passive energy sources around us and actually use them to reassemble new physical objects. So the left one shows how you can use, for instance, kind of magnet concept where you have negatives and positives attracting and then snapping together as elements. And on the right-hand side, you can't actually see that here. Sorry, it's the right-hand side of my screen. Here you actually have a form of computing where you actually compute a shape by manipulating those rotational axes of those in-between segments between the solid ones. And by rotating them in different ways, you change the way they fold, and you can create from basically a linear strip a three-dimensional object. And they call that 4D printing because it's moving. But that's a little bit of a marketing term, I think. But going back to traditional programming, if we look at the family tree of history, the history tree of languages, you can actually see how much crossbreeding and influencing there has been going on throughout the last 50 years. I don't really believe that last part of the graph is really true. This is especially the last few years, there have been so many new languages appearing on the market. They are probably not really being taken into that research here, but in general, it's very interesting to see how many languages there are available. So another view of that system of programming languages is this one. And when we zoom in, we can see here what really are the main contenders. And if we think about our field of creative programming, then we actually only use not even a handful of them most of the time. And that means, bearing in mind that every language has this different view of the world, we actually really just see the world through those really narrow lenses of those languages, and we ignore everything else out there. And then there are also things to bear in mind like that. So object-oriented programming is the de facto standard of programming these days, and it has a lot of problems, believe it or not. And especially if we compare to all the developments going on in the more physical side of computing, hardware and the Internet of Things, then we really have to start thinking about other options and also be open to those options and actually understand how all those different things fit together. So here's a similar graph done by the same person, where it's more a comparative graph, how showing the relationships of different approaches of programming. So we have all the object-oriented programming families, imperative, procedural, functional. So these are all different concepts of those worldviews. And again, right now, these are the main contenders in creative computing. There's also Cinder, which is not shown here. I used the Open Frameworks logo as a all-encompassing C++ approach. But there are a lot of other newcomers, and they are very, very interesting all in their own right. And often we think Java and processing are kind of the easiest to learn languages, but it's, I think, not necessarily true anymore. So if we kind of zoom out and think about what is the basis of computation, it really is just input, process, output. And then the next question is, okay, what is a process? That's also not really true, I have to say, in a lot of programming languages. So a process is really just algorithm and data. And to understand what that means from a more language point of view, we have the so-called Ogden's triangle, which has been invented in the 1920s. And it's just a kind of theory of how communication can be, or what are really the stumbling blocks of communication. So if you say you are a book author and you have an idea and you want to write your novel, you have to use language, which is the sign or the number of signs, to encode those thoughts, write them down. Someone buys your book, reads it, but then has to decode it into the original concept again. And at every of those arrows, information is being lost. Yeah, the Chinese whispers problem, you say one thing, but that's not necessarily same thing right now. What I'm telling, what is absolutely clear on my mind, might be total gibberish in yours. I hope it's not, but there's a high possibility. So that's the same problem we have with computing. But the interesting thing with computing and programming especially is that algorithms themselves can be nested infinitely. And you can visualize them as kind of hierarchies, so where every process is really just depending on a lot of other data and processes. You can apply this to ideas or creativity in general, where we can actually, if this is a good model, which I here ask a question, I'm not saying it is, it's very simplified, but if we would say hypothetically every idea is just the result of previously existing ideas in the environment and the combination of our own memories, then where does intellectual property fit into this tree? Does it mean someone owns an entire branch of that tree and no one is allowed to touch it? Also questions about, so we talked about the basic of programming, of computation. Basis of programming is to not repeat ourselves. Yeah? Einstein said that a long time ago. So this was really the impetus why we wanted those machines in the first place. And now that they are there, we have now a new kind of fragmentation in society where we have people who are familiar and pro-technology, and we have already starting the kind of anti-technological trend where people go more towards rejecting technology at all costs. And I think as a species, the use of technology is the only major thing which has set us apart from all other things on the planet. If we used stones, that was modern technology of the day. These days, modern technology of the day is those kind of machines as a general mass. And I think if you want to call yourself a human, you need to have some form of familiarity with that technology to figure out what are the good ways apart from what corporations dictate. Those machines have so much potential for all sorts of communication, yet if we only become passive consumers of those machines and let those machines take over processes and decisions in our own lives, we become slaves to them. And I don't think anyone in the room is interested in that aspect. So I think it is absolutely essential that education needs to hit more to teach computation as a general approach to life, really. So if this is all true, then it really is not so much about the processes anymore directly, it is actually about what happens to our data. So data is the most abstract form here for ideas or any form of media. And how is that data being transformed over time, over the different steps? So I'm skipping a few things here. So one example I often use is the C machine in New Mexico. I've been previously assuming it was in California, but it's in New Mexico. It's the world's biggest plasma generator. And what you can see here, those lightning patterns are a snapshot of a process called diffusion-limited aggregation. So this is how molecules in lightning, for instance, form in the atmosphere, or how lightning forms through the molecules in the atmosphere and creates those kind of patterns. But a more general, unconstrained process version is so-called Brownian motion. And you could actually describe this is running code. You could actually describe this to a machine like this, that we take an infinite number of random points in space. We take then, say, 500,000 of them. We add them all together, so that gives us a path through space, which is random. And then for every point on that path, we create a sphere. We merge them all together, get a 3D mesh. And then we can render that, and we get something like this. So this is just a single particle recorded over 500,000 time steps. And this is total noise. There's no information here. It's chaos. So if we start constraining that process by, for instance, allowing particles only to align in certain directions, then we can start forming already more natural-looking objects. And we can take that further to align on curves. And when you have that step, you can actually align it to Bezier curves and recreate typography out of those particles. And it's literally hundreds of millions of those particles. Here's another thing I need to skip now, because I had some problems earlier in the hotel with the internet. So it's, again, here's some more different languages coming into the play. And a concrete example was a project I did earlier this year for the Leeds College of Music, which is English music college. And this is basically their identity generator they got. And you can create things like this with it. Why is it not playing? This one's not playing either? OK. That's not good. Maybe. These should have been videos, but hey. They're actually sound-reactive versions of that sphere. I might find one later. I don't want to disturb, take too much time now. So, and to render those videos, each of those frames can contain up to 720 million points. So that is a few billion points per minute. And this is far too much computation to do on a single machine. So to not have to wait or block your resources in your office, that whole rendering aspect of those videos has been moved into the cloud. So on Amazon, so the client simply gets this web front end, and they have the desktop application to create a new version of the logo, and then upload a video and a piece of music, and it creates those videos on demand online. So it's a nice workflow, and it's very resource efficient as well, because you only pay for those extra hardware resources if you actually need them. So this was done in a language called Clojure and OpenCL. And the reason why I chose those languages is because they allow me to use my machines I have available to this efficiency. So if you look at the bar graph at the top, you can see it's a 16-core machine, and every processor runs at full capacity. So it's the maximum you can use a machine for. And we really need to have more languages which actually allow us to do that. Because the more we talk about bringing machines in everyday environments and have more of sensors here and things there and mobile phones here, the more we really slowly hit the energy barrier. And there's a limited amount of lithium in the world. And we really need to slowly start thinking about what that means for all the, for instance, mobile devices if they are not constantly fully used. So also in talking about different processors, I'm sure some of you have heard about Moore's law, which is basically not a true law. It's a hypothesis that every roughly 2 years or 18 months, our compute power is doubling and the price is halving for that new power. So and this has been true for the last few years, last 40, 50 years. And a lot of people think it is slowing down slowly, because what has happened in the last recent years is that in order to make computers faster, we can actually not make them more integrated, but we only can add more cores and make them more parallel. So here you can see, as I'm stepping through those film images, which are actually the dies used to produce chips, you can see we are now partly at 128 cores, and this is actually already really old. So this is a chip which has 128 chips in its side. And that kind of new hardware requires an entirely different way of thinking about programming and all the things we are used to, actually. And then on the other hand, you have a new development, as I said, which goes more into ambient mobile devices. So we have the Arduino, Raspberry Pi, but there's a whole new generation of alternative computers, really. And the important thing about those is that they are super cheap. So Arduino costs around 15, 20 euros. Raspberry Pi, 25 euros. And you can have a lot more of them, and they have partly very, very high compute power as well. So, but these are still traditional ways of computing. And what is slowly happening in hardware at the moment, or for the last few years, is that we have slowly getting towards the reconfigurable computing architectures. And that means that we are not just now be able to write algorithms through software anymore. We can actually write a program which actually configures a new hardware inside the chips we are using. So that means, depending on what our application is, we can write a program which actually recreates a new chip on demand as it's running. So, and this will change everything. And even for those kind of processors, we already have Kickstarter projects, for instance, Parallella, that is right now able to be pre-ordered. It costs $99, uses between 2 and 5 watts, which is only about, well, between 20 and 40 times less than what a normal processor uses, but is almost as fast as a normal processor. You can build clusters out of them. You have things like application-specific hardware, like for instance here for Bitcoin mining, USB sticks. They can also be clustered. Those white things are fans because they get super hot. So this is how people make money. For instance, I don't know if anyone follows Bitcoin. It's maybe slightly off topic, but Bitcoin has been exploding in price recently, from a $5 exchange rate to over 1,000 within a week. So someone got really rich 2 weeks ago. And then we have also things like those field programmable gate arrays, which is basically the kind of chips I was talking about, where you have millions of those logic gates within, and you actually can write software and reprogram them and implement, for instance, your own processor on top of that. So these are, whenever people talk about the Internet of Things, we often talk about just emitting data, sending data from one point to another. No one ever talks about what happens to all that data. What actually do we want to do with that? And I think a lot of the reasons that the question can't be answered yet is because people keep on thinking about using super low-tech devices where you can't really embed much of a compute power in the environment. While if once the moment comes when those kind of hardware will be affordable and cheap, which will be in the next few years, you can actually have really starting to have intelligent environments, because those kind of hardware setups can encode far more complicated algorithms. So, and another way in software is also to have different ways of thinking about programming in general. So what we often do is that we have an idea, and then we have to break that idea into tiny steps, which are so small that they can be written as a piece of code to the computer. But a totally different way, what we really would want to do is to have just an idea and describe what are the elements, and we allow the computer to figure out how those things should fit together. It's far more human, but it's an idea which has been dead in the water for the last 50 years, because back then hardware simply wasn't powerful enough. But what I find really interesting is that a lot of those old ideas are now actually starting to become viable. So an example here is, for instance, we want to do some, for instance, natural language programming. So someone types in a language or a sentence, and the computer or the program needs to be able to know if this is actually a sentence. So you can define the grammar rules of English. So what is a sentence? It's a noun phrase followed by a verb phrase, and then blah, blah, blah. And then you define a little vocabulary, and then you actually write the same thing again as code, and then you can ask the computer, okay, here's my sentence, a man loves a woman. Is it a sentence according to your grammar? Yes, it is. But then you can also turn this around and say, okay, you know what the rules are, and I want to know now what are all the possible sentences for those rules. So that is actually the inverse. So that what this creates, this step, is that it gives us a map of the entire design space. If we not now apply this to just language, but imagine we have a generative design set up where you have different parameters, and you want to understand all the interactions between those parameters, you could use that kind of programming where you actually didn't program anything. All you did was describe how things should fit together, and the computer will show you a map of what is possible. And I think this is, as I said, a very underexplored way of thinking in our field. And considering we call ourselves, or a lot of us in the room, I assume, call ourselves creative programmers or creative coders, then we really should be showing a bit of creativity. So the kind of thinking also applies to the what I sometimes call next generation of the web, even though this is a totally overhyped phrase. But the semantic web is basically boiling down to expressing data as English sentences, or using the basic subject, predicate, object form. And by doing that, so by saying, I'm a person, or my name is, or I am in Düsseldorf, these are all short single sentences. And if we collect all those sentences, we can add them together, and we can have one object referring to another sentence, and so on, forming one big graph, which contains already by now a few 100 billion of such statements, and all of them can be queried. So this is slowly growing in the background, and thankfully a lot of research went in it so far. There's been an active development for the last 10, 15 years. And we recently started working with the Open Data Institute in London, and we had the opportunity to create some visualization based on open data about London, which was used for their annual summit. And that image, that video which you see here now, is basically a map of London boroughs, and it's an animated heat map where you can see all the ambulance cases per month which are related to assaults. So basically any form of violent crime victims. So what that shows really is a map of London showing all the troubled hotspots over time. So in that whole map then also has been used as a form of identity, which is still kind of in the works. And now having this defined, so that entire animation is completely generative data-driven. There's not a single manual design element involved in there apart from that wordmark logo. So I think this is the kind of work I want to go more into the future, and there will be an announcement sometime in the next few months, because right now it's still too early to talk about it in detail. So back to different languages. So this next project was done for Google, and in collaboration with a lot of other companies, including tellerrand and BeReal, who did the website, and tellerrand were the main contributor to this project, really, and also initiator. So what you see here is an exhibition at the Science Museum in London, which was on from summer 2012 to summer 2013, like this year. And it was 5 experiments, physical experiments, all linked to online experiences, and also mixing things what people could do on the website. So you had the same experiments online as well, and people could interact between the two worlds. So we had mechanical instruments, we had those 360 video periscopes, and those other things you saw. So, and one of the key elements in that exhibition was that every visitor, both online and in the museum, got those kind of lab tags, which are little badges people collect at the entrance. And those tags each have a different symbol. So every visitor has a unique constellation of those symbols, and then those visitors have been visualized on that wall. And that was combined with a projection combined with an industrial robot, which was then drawing outlines around the different visualization modes. So, and altogether, I'm not now going through this, but altogether that was roughly 25,000 lines of code, and actually involved use of all those languages. And that was a really long project, probably the longest project I ever worked on. But I just want to talk a little bit more, also going back to the zeros and ones, and how something which is often considered super low level actually is a really important knowledge to have in this project when it came to the design of those computer vision markers, which ended up being on the lab tags. So these are all some really early prototypes of me trying to figure out how can you create a custom computer vision marker system which also potentially fits within the logo shapes of the web lab. And they could be arranged like this, but then because of production costs with die cutting, this would have been far too expensive. So it became more something QR code-like, but possibly more flexible than QR codes, because you can use a lot more space for custom designs than in a QR code. And then we finally maximized that inner space and reduced the machine-readable part, so that dot pattern on the side. So, and then this had to be implemented in 3 different languages. First in Java and OpenCV for the museum, because that has the best performance. And then we did a Flash version, and then WebRTC came out, and then I did a JavaScript version with WebGL and GLSL to rewrite that code there. So, and the idea is that basically you go to the museum, you get your tag, you do those experiments, and then you can take that thing home and go to the website, hold your tag in the camera, and it will recall all the things you have done in the museum, and you can share with your friends and family. So it's now back to the kind of transformation pipelines, and also another example of mapping out a design space. So what we have here is a process called Gray-Scott reaction diffusion, and it takes 2 parameters, and you imagine them as ingredients for a chemical reaction. So if you increase the concentration of one ingredient towards the right and the other ingredient towards the bottom, you basically get those different patterns. And you can see that most of that design space is really just empty or unusable. So you only have that hotspot region of interest in the middle, the diagonal. And if you combine that with, for instance, mask, you can then say all the points within the letter shapes get a different set of configuration than the points outside. And because of those different configurations, and because it's a time-based process, it creates a different pattern as a result. So what is really interesting about this patterning process is that it only appears by every pixel looking at its 4 neighbors, nothing else. All that macro behavior, walls forming, dots splitting into slowly filling up all available space, is actually not designed by me or by anyone else, really. It's just appearing through pure interaction of neighbors. And I find this really highly fascinating. And when you start recording those frames of that animation and stack them up in 3D, so you have the time axis going upwards here, You can then see also how those dots split over time. And if you start with an outline, you can then get something like this, 3D printed, and get it on the cover. So, and it really feels like sandstone. It's 3D printed with actually the cheapest 3D print technology there is. It's this powder injection. And by now, this is 6 years old. It actually has really almost browned a little bit. So it really feels like a coral now if I take that out. But what is interesting about this design approach is that it's all done with voxels. So basically the 3D version of pixels. And voxels, most of you probably know from Minecraft. Who's playing Minecraft? No one? No. You're lying. Who's got kids? Yeah, are they playing Minecraft? Yeah, there you go. Thank you. It's not just mine then. So voxels are super amazing because unlike in Minecraft where they are this size in the game world in relation, you can actually make them as small as you want. And if you have really small ones, you can create amazing surfaces out of them, which you could never create with any other design tool. So, and one thing that was a research I did earlier this year was to trying to think about how we can solve problems in 3D printing when you often have solid objects. So what you see here is on the left-hand side is the code which creates the object on the right, but the object itself is a three-dimensional version of a chain. So a one-dimensional version, a normal chain, as you know, is only one-dimensional. It has freedom to wiggle. This one actually interlocks in all directions and is therefore super stable. So if you would print an object like this, right now you would have not much control over what is going on inside unless you design it manually. So here would be, for instance, that process applied to the insides of that object, reducing material use and also making it far more lightweight and stable. And because it's parametric, you can have it at different scales, whatever you want. You could apply it to itself, so this is a kind of recursion. If you do this few more steps on top, you would end up with fibers which are so thin that you would get textile. And because of the interlocking, you can actually really get to that level. Right now, printer resolutions aren't high enough to do that, but it's just a matter of time. Also, another interesting thing of voxels is that you can define them as a hierarchy again. So if I add detail, you can get better and better surfaces. And then you can do things like this, hollow out super complex objects. And the reason this is very, very easy to do with voxels is because you can always imagine those as a stack of 2D images, and then you can just apply 2D image filters on a 3D model, slice by slice. So this is kind of the edge detection filter in Photoshop applied to a 3D model. Or here you do the opposite, you just keep the spine, and again, do it at different hierarchies. So another project using voxels was done for Universal Everything, for an exhibition in Paris. So here you had the design tool, where you actually only have lines in space, and those lines are obviously connected with a system. So you have those 40 or so parameters which define basically the position of the hip bone, the knee bone, position of, or the tilt of the foot, of the neck. So you had quite a lot of different parameters. And then there was a super simple physics simulation which ensured those things actually can stand physically. So because if they are 3D printed objects, on screen you can do whatever you want, but if you print them, they need to stand up. So apparently that didn't work in all cases, but most of them did stand up. And they were then printed in different materials as well. And I think I'm skipping this because I'm running late. So here's a nice bunny, but this is where you can find me online, and I'm done.